Okay, we're continuing on with part 3 of 3A1, chapter 5. For this one, we're jumping back to objective 2. And the objective 2 says define power and mechanical efficiency, calculate power expended when work is done, plus the power developed and mechanical efficiency of a reciprocating engine. Okay, so we got a bit of work to do here. First thing, we need a bit of definitions and some equations. So first of all, what is power? Well, power is a measure of energy by time. So now we talk time, so any place where we have seconds, hours, we've got power. Units are going to be energy, so joules per second, and that has its own unit, which is known as a watt, so capital W, which is a watt, named after James Watt. Okay, so force of 1,000 newtons is required to pull an object over a distance of 10 meters. If it takes 5 seconds to do this, what is the work and what is the power? Okay, so first thing we're going to do is we're going to find the quantity of energy, which in this case would be work. So we have a few different ways that we could describe energy: heat, work, potential energy, etc. In this case, we have work as the energy that's going to go into our power equation. So work is equal to our force times our distance. In this case, 1,000 newtons, and the distance of 10 meters, and we have 10,000 joules of energy in the form of work. Okay, so power is equal to energy by time, which is equal to 10,000 joules per 5 seconds, and that would leave us with 2,000 joules per second, or I guess watts. Okay, we have a kettle, and on the kettle it has a rating of 1,200 watts. How much heat could it produce in 12 minutes if we let it run for 12 minutes? So in this case, we have power, which is equal to energy, or I guess our heat, by time. We have one complication, which is that we have minutes. So 12 minutes times 60 seconds per minute is equal to 720 seconds. We'll need to rearrange this equation to solve for energy. So my heat is going to be equal to power times time. 1,200 watts or joules per second times 720 seconds, and that's going to give me a value of 864,000 joules of energy. We have another typical question in this section. Pump is required to lift a certain amount of water through a height of 35 meters. What must the output power of the pump be in kilowatts? So this looks like it might be a thermo kind of question, but it's not. It's an applied mechanics question. Just has a pump in it. So we just describe what's happening. We've got some sort of reservoir, and we've got an upper reservoir, and I guess we got some water in there. Great. And we're going to have a just going to pump it up from the bottom reservoir. Overall, we have 35 meters of height, and we have a certain flow rate. So first thing that we're going to do, yes, we do have a tons per hour, but what I'm going to do is I'm going to ignore the hour for now. So I'm going to say, let's just consider 1 hour of time. So in 1 hour, we know that we would have lifted 40 tons of water through that height. So how much energy did that take? Well, I have 40 tons times 1,000 kilograms per ton times 9.81, which is gravity, times 35 meters of height. So just like we did before, we have mass, we have gravity, we have height, and that gives us an energy. And if we calculate that out, what we're going to find is we get a whole lot of energy. 13,739,000 joules of energy. Okay, we want to know the output power of the pump. Okay, so how much pumping power is required. Not over an hour, because that is measured in seconds. Okay, so 1 hour is equal to 3,600 seconds, which means that the power is equal to the energy by time, and we get 3,815 watts, or in kilojoules, or sorry, kilowatts, 3.8 kilowatts. So that's the pumping power that would be required to move the water from the lower reservoir to the upper reservoir over a span of an hour to move 40 tons. Okay. We have a second question is, well, if the pump was only 65% efficient, so how much power would we have to supply to the pump? So before, when it would be 100% efficient, we would need 3.8 kilowatts of energy to move that water, and we could supply 3.8. But if the pump's only 65% efficient, what that means is we're going to have to supply more energy to the pump in order to get an output of 3.8 kilowatts. When we talk about efficiency, efficiency is always a measure of what do we get compared to what do we put in. So what's our output compared to what we put in? Okay, so output always less than our input if we have an inefficient machine. So in order to find what we have to put into this machine, my input power is going to be equal to output divided by efficiency. 3.8 kilowatts divided by 0.65, so efficiency as a decimal place, and my final answer ends up being 5.9 kilowatts. So an inefficient machine means that I have to supply more energy than the energy required to move that water to the top of the hill. So we figured out that calculation for mechanical efficiency. Sometimes we use a symbol like that for efficiency, which again is your measure of output compared to input. Okay, and always this guy as a decimal. So often given as a percent, but we use decimal for our calculation. So one more sample question. We've got an electric winch on the roof of a building, and we have to raise some object. We have a certain amount of time, and we have an efficiency. How much power must be supplied to the winch? Okay, so first approach, what we're going to do is we're going to figure out how much work does it take to move this object from the ground all the way up to the top of the building. Okay, so if he's going to go up to the top of the building, the work is going to be equal to the mass times gravity times height. So 0.7 tons is 700 kilograms times 9.81 meters per second squared times my height of 80 meters, and that gives me a work of 549,360 joules. Power, what I'm going to find is the power required to just do the work, so without looking at the winch. So the power is going to be work by time, or energy by time. Okay. I have 3 minutes, so 180 seconds. So 549,360 joules per 180 seconds is equal to 3052 watts. So that would be how much power would be required if my winch was 100% efficient. However, it's not. So my efficiency is equal to out compared to in. And I want to know a new input power. So my in is equal to out divided by efficiency, 3052 watts divided by 0.78, and I have a value of 3.3913 watts, or 3.9 kilowatts. Okay, we have one other component to cover off in this section, which is power in a reciprocating engine. Okay, so if we talk about a reciprocating engine, pardon me, what we would consider would be a piston inside of a cylinder. Okay, so we have a piston inside of a cylinder with pressure acting on it. It will create a force, and as that piston moves out, because of the force acting on it, it will create some work. Problem that happens when we talk about work is, in order to find work, we talked about a graph, and we said, okay, if we had force and it was consistent, okay, or maybe we didn't have it consistent, maybe we had it that it was gradually increasing, and we had a solution for these things. Okay, here's our problem with this arrangement. If we think about what happens to the pressure as it is consumed, our pressure starts up high, and as the the piston stretches out, our pressure changes, and we kind of have a curve that gets created. And so it's difficult for us to figure out exactly what happens with the pressure as we go along. This would be a calculus problem where we subdivide this into a bunch of different slices and we figure out what happens at each slice, and we don't want to make that much effort. Okay, so what we do is we introduce an idea of, in order to simplify, is we come up with an idea known as the mean effective pressure. Okay, and what we assume is, if we considered that throughout the whole sweep we had some pressure, and it was some averaged pressure throughout. Now all of a sudden we have a shape that we can use, that we can calculate, because we kind of have that idea that we could find the area underneath that curve and quantify it as an amount of work. And we call this the MEP, or the mean effective pressure. Okay. And we use that in a lot of different machines. So this would be one case where we have a stroke, but more likely what happens inside of a machine is that we have a bunch of different strokes. So we have a combustion and or a compression, an expansion, exhaust, intake. And so no matter what kind of engine we have, we may try to find what is that averaged pressure, and that would be our MEP point. And as long as we can find that averaged point, then we can calculate how much work an engine is doing, and we can compare engines. Okay, so let's look. We have an equation that's available for this that's in your supplement. Okay, indicated power is P times A times L times N. Okay, so first of all, what we have is PM, which is that mean effective pressure. All right, we have area, which is the area of the piston. And these guys together create our force, okay, because pressure is equal to a force per area. So a force is equal to pressure times area. So you can see here you have pressure times area, and that really is your force. Okay. Force times distance gives us energy, and L is what's known as the stroke. Okay. And the stroke is the distance that the piston moves from what's known as top dead center to bottom dead center. So as the piston moves back and forth, one length would be known as L, which is the stroke. Okay. And then the thing that turns it into power, because P times A, the force times the distance, is work, and then we have N, which is a measure of how fast is that engine working, or how many strokes is it going through per time, and that gives us power. Okay, and so N is listed as the number of power strokes per second. So you have to be careful if you're given RPMs or something like that. Anyway, let's see if we can answer one of these questions. Okay, so find the power developed in kilowatts by an engine that has a piston area of 300 centimeters squared, a stroke of 50 centimeters. The average pressure on the piston is 400 kPa, and the engine makes 220 power strokes per minute. Okay, so let's figure that out. So first of all, I'll go to my supplement and I'll get my equation. IP, indicated power, is equal to PM, mean effective pressure, times area, times my length, times N. All right, so PM is going to be equal to 400 kPa, and I want to make sure that these are all in my base units, so 400 pascals, which is a Newton per meter squared, 400,000. My area is equal to 300 centimeters squared, and I've got to be careful. Centimeters squared is a real trap. I want to make sure I divide twice, and by centimeters to meters conversion, divide by 100 twice, and what I should end up with is 0.03 meters squared. I have L, which is my stroke, 50 centimeters, which is equal to 0.5 meters. And I have N, which is number of power strokes per second. So it says 220 per minute times 1 minute per 60 seconds. Gives me 3.67 power strokes per second. All this info is going to go into my equation. So 400,000 newtons per meter squared times 0.03 meters squared times 0.5 meters times 3.67 per second. Indicated power ends up being 22,000. And then from a units perspective, looks like meters squared cancels out, and I'm left with Newton meters per second, or that would be a watt. In kilowatts, 22 kilowatts. If the engine has an efficiency of 82%, what is the total power output from the engine? So this would be the input from the cylinder, and I'm curious what the output would be. So my efficiency is going to be equal to my output compared to my input. So that means my output from the engine is going to be equal to 0.82 times 22 kilowatts, or just about 18 kilowatts. Okay, that's it for this module. I'll see you on the next one.